Welcome to MRS Bulletin's Materials News Podcast, providing breakthrough news and interviews with researchers on the hot topics in materials research. My name is Sophia Chen. Marina Galliani and her team have designed a wearable step counter, which can be incorporated into a sock. It counts your steps because it's got flexible electrodes on it that complete a circuit when you put your foot down.
We are measuring the open and the closed circuit date of our device.
Galliani's key innovation is the material that makes up the electrodes. She's a materials scientist graduate student working in Esma Ismailova's lab at Mines Saint-Etienne. They're working to create biocompatible, eco-friendly materials for wearables, as Ismailova explains.
We try to combine organic electronic materials with biology at different levels.
For this particular project, they developed a conducting material that they can make using an inkjet printer. This means they can fabricate devices by printing, which uses up less material than traditional manufacturing methods.
We're reducing the waste generation by processing these materials.
They made the material based on a commercial polymer known as PEDOT-PSS in a water-based solution. They combined it with various solvents to tune the electrical conductivity. The conductivity is based on the shape and structure of the polymers in the material as they dry. So to tune the material's conductivity, Galliani alters the solvents in the material. This changes the alignment of the polymers in the material as it dries. They tested the material's conductivity on several substrates, including paper-based substrates and textiles. To make the material printable, they also needed to tune the material's viscosity.
Since we start with a water-based solution, this fluid has surface tension that is close to water. In this case, for inkjet printing application, this value is too high. Surfactant is mainly used to reduce the surface tension of the liquid.
To characterize the material, they ran many different tests. They tested the material's ability to withstand wetting.
Imagine you're wearing this device against your skin and you're sweating, so sweat can actually dissolve the PEDOT-PSS itself.
To keep the material from dissolving, they added cross-linker to the material to help it link with the substrate. They also tested its mechanical properties by bending it. They were able to bend the material over a radius of 800 microns, which is beyond the usual requirements for wearable electronics.
The bending radius in the flexible electronics is set to 1 millimeter.
To test its biocompatibility, they put the ink on a glass slide and cultured human stem cells on top of it.
In our case, the cell will continue growing and develop as a normal to the standard way.
Other than the material itself, Ismailova says that they've developed a framework for designing and evaluating biocompatible organic materials that others can use. For future directions, Ismailova says they want to find more applications for the material. She's open to collaborations in industry to scale up the material. Because the material relies on inkjet printers that are already commonly available, this material is relatively easy to incorporate into industrial processes.
The processes that we use here are quite straightforward, transferable to industry.
This work was published in a recent issue of APL Bioengineering. My name is Sophia Chen from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org and follow us on Twitter at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.